Hello, my name is Jonathan Mesa, and this is my final project for ECE 178 Embedded Systems at Fresno State. Before we get too into the project, I would just like to go over a quick overview of what will be discussed in this video. First, I'd like to go over the background of the board that I'm using. Additionally, I'd like to speak about the software that's being used along with the board. And then we'll transition into the project description of the custom CPU core, the high-level game structure, also low-level structure, and finally I will show a demonstration of the project. And so we will begin with a bit of background on the hardware and software used in this project. The actual board used for this project is an Altair FPGA DE2 board. This board has been used throughout the semester for a variety of different assignments and labs. A bit of the specifications include a Cyclone 2 2C3F FPGA chip. Additionally, it has serial configuration, 512K SRAM, 8 megabyte SDRAM, 4 megabytes of flash. Additionally, some of the hardware components includes SD card socket, 4 push buttons, 18 toggle switches, 8 red and 8 green LEDs, in addition to 40-pin expansion headers, and much more. And here's an image of an actual Altair FPGA DE2 board. As you can see, it has plenty of hardware components for any assignment that you could possibly hope to confront. As you can see, there is components for displaying, whether that be LCD, whether that be just 7-segment displays. Additionally, you have input and output. You have your LEDs, your flip switch buttons, your push buttons, and as mentioned before, your 2 expansion headers. You do have room for reading through RS-232. You have Ethernet, VGA out, and a plethora of other hardware devices. Those of you who are familiar with the Altair development board should already know about Quartus and QSYS. Quartus is the main software used for analysis and synthesis of the hardware description language designs. It gives you the ability to compile, do time analysis. You can actually design simulations of the hardware itself and a host of other features that can be used for development in FPGA. One of the ways we actually can do custom CPU cores, which is what we do for this project, is through the use of a system tool called QSYS. It is a system integration tool. It's a next generation SOPC builder, and it uses FPGA optimized network on a chip architecture, letting you reconfigure, rewire, and do everything you need for a custom CPU core. Next, we will go over a description of the actual project itself. As previously mentioned, this project uses Quartus and FPGA to construct a custom CPU, and some of the components that the CPU uses is parallel I/O for inputs such as the flip switches, the push buttons. You can even use it as an output for the red and green LEDs and for the 7-segment displays. Additionally, you can use it for general purpose in the case of GPIOs. In addition to that, you also have your SD card socket for this particular project, JTAG UART, as previously mentioned, 7-segment displays, and interval timers. Additionally, you have within the program aspect itself, you have support for hardware interrupts, whether that be for the parallel I/O, those are edge triggered in this case. Additionally, you have your 2 timers with different accuracies, one to the millisecond, the second to microsecond, and as alluded to before, there's also room for general purpose I/O. So in Quartus, here is the processor block diagram. This is of the custom CPU core. As you can see, you have your different buttons, switches, LEDs, hex displays, GPIOs, SRAM, and SD card reader. Previous slide of the block diagram of the CPU core was actually just a high-level view. If we actually go further into QSys, here we can see the system connections, and we can see the different characteristics of each of the components that are currently being used by this custom CPU core. And you can see the different interconnections, the IRQ levels. As you can see, for this particular core, we do have up to 5 different IRQs available to the user. Of course, this being an FPGA, you can go in and change this to allow for every single one of the PIOs you see present in this system to be used for interrupt purposes. So now that we've discussed the custom CPU core, its high-level design, its interconnections, I would like to talk about the project itself. I ended up deciding to go with the state machine, specifically the Moore state machine. For those of you who don't know, it is a sequential finite state encoding. Its output is only dependent on its current state, and for this reason it's very simple, but in comparison to Mealy's state machine, it uses more states. The mechanism that drives the input is the interval timers that were previously mentioned. On the timer timeouts, states are checked. In addition to that, whenever the user uses the push buttons or the flip switches, these are also considered inputs as well. The only high-level portion that's not really considered an input is the SD card itself, but I thought it would be good to mention it here, since it is an integral part of the game itself, being that it's used to store the highest score by the user during the process of the game. So as a continuation of our overview of the high-level structure of the game, this is the finite state machine map that displays the flow and logic of the game itself. As you can see, when the processor starts up, it starts at its initial state and then continues into S0 and then into the rest of the game, which is, as you can see, is almost entirely dictated by the user's inputs and different timer interrupts set up through the logic of the game. During the system demonstration, we'll go over more specific detail what each of these different states represent. Now we'll dive a little bit deeper into the structure of the game. The code is actually separated into 2 files, one being a main file, the second being an exception handler file. The main file does most of the clerical work, such as initialization of components, of interrupts, and of course holds the data used by the game itself. The exception handler file actually houses the majority of the game logic, and we'll actually get into that more. So to further get into the exception handler logic, the FSM is actually driven almost exclusively by the interrupt service routines, and that's selected based on the IRQ level triggered. Additionally, once we reach the appropriate interrupt service routine, we go into a subroutine based on the current FSM state, and again, we'll get into that in a moment. So here we can see the flow of the main file. We have, of course, the starting port, the start of the program. Part of the initialization includes enabling interrupts such as timers, flip switches, push buttons, interrupts. Of course, because the SD card is integral to keeping track of the highest score, we do have to wait for the SD card to load initially before doing anything else. And once the SD card is finally in place, timer is actually started, and this timer is used to find an RNG seed that can be used throughout the game to generate the different patterns that are going to be displayed on the LEDs. And once this is finished, it goes into an infinite loop where it waits indefinitely until an interrupt is triggered. And here we see the low-level flow of the exception handler routine. Of course, once the interrupt is triggered, the exception handler is entered here. Of course, before we do anything else, we have to check which IRQ actually generated the interrupt, and this is done through checking on Altera board. You check the iPending status register, and once the appropriate IRQ is determined, of course, we have to go to the appropriate interrupt service routine. And once we enter in that interrupt service routine, we check the current state that we're in, and this moving forward helps us decide what should be done next to service that actual interrupt. and it is here where the majority of the game logic is housed. So once we find the source of the interrupt and the current state that we're in, we know how to appropriately determine what to do next. So now that we've gone over the hardware, the software, and the high-level design of the game itself, I'd like to demonstrate the actual system in action. So here we have the Altera board. We've already connected to it, as you can see. We've downloaded the system onto the board itself, and as you can see, we are going to compile the code, and once it's compiled, we should be able to run the program and demonstrate the system fully, and there we go. We'll just let it run, and let me explain the process a little bit. First, in order to start the game, you have the two push buttons. You'll have to press clear to get from that initial state and to have a message displayed on the LEDs. And then afterwards, you would have to press the start button in order to actually start the game. And at that point, the hex displays will display the score for the current round, and the LEDs will light up with the pattern depending on the RNG seed at the beginning. And the purpose of the user, he'll have to flip the switches in order to that correspond to the LEDs that are active, and this way they'll pass each round. Additionally, if you press the wrong switch, that'll end your round. Your top score will be displayed here on the green LEDs. So I guess we'll just give it a shot now. And there we go. Hello. And now we're going to press the start button, and that means that the round has begun. And now we just have to wait until the LED display. And now we have to try to get all of the, well, if you notice, the LED, the wrong flip switch was pressed for the wrong LED, so that means that we're out, unfortunately. We'll have to restart it clear, press the start button again, and wait for the LEDs to flash. And if we're able to get them all, we proceed to the next round, and as you see, the display keeps track of the current score. And again, if you notice that we took too long, we were able to get everything correctly, but because we took too long, we also lost this round, so we have to start all over again. Now we just wait for the LED switches again. As you can see, we've beat this round, and we'll proceed to the next round. And again, this round has been completed, and we'll just wait again for the next round. So currently we are tied for the highest score, so the high score won't get updated yet. We just have to beat this next one. And now that we've beat the high scores, you'll notice over here on the green LEDs, now the score has been updated to 4, and we'll go through again, and as you notice, we got the wrong ones. So now what we'll try to do is we'll try to reload the software onto the Altera board, just so you can see that it restarts properly. So here we go. We're reloading the software onto the board. And now that the software is reloaded, we'll try to start the program over again. And as you notice, the previous high score of 4 is now present on the board. So as you can see from a demonstration of this project, the use of interrupts from the PIOs and the timer was able to be used successfully to create a game. And in addition to that, we were able to incorporate the SD card, which is something that we learned near the end of the semester. And overall, I feel like it shows the integration of the knowledge that was gained throughout the semester, interrupts the different hardware components, and even the external devices such as the SD card.